Good morning, everyone. Do you hear me? All? Okay, good. So welcome to the second day of the Scholar 2, the conference in celebration of the Ram Murthy's work and legacy. So before we start with the talk today, I have two announcements. First about the banquet. So tonight we have banquet. It's not in this place, in the Metropolitan University. If you haven't gotten your ticket, please come and talk to me. We have all the tickets are complimentary, so it's free of charge. So please come and see me. The address is there, so you can. I think walking distance probably is about 20-25 minutes from here. We are going to try a take two pictures because yesterday I didn't have my hat, so today I brought my hat. And so some people actually told me that they missed that picture. So after the morning session, we're going to try again. And also the weather is much better. Okay, so that was the announcement. So our first talk today is by Ritabrata Munshi from Indian Statistical Institute. And the title is QUE for Powerful Level via Shifted Convolution Sums. Thank you. You can start.
Thank you. Thanks for the introduction. And so I'd like to first thank the organizers for their invitation. It's a real pleasure to speak in this occasion. So the topic is quantum unique ergodicity in the level aspect, and we'll try to prove it using shifted convolution sum. Right? So let's start by recalling what the quantum unique ergodicity says in the arithmetic setup. So let F be a holomorphic cuspidal new form for the full level SL to Z of weight K, say. To F, we can associate a measure on the modular curve x01, which is the upper half plane modulo SL to Z, by defining, so if you pick any measurable function on x01, you define mu f phi to be the integral over the modular curve of phi z multiplied by fz mod square y to the power k d mu z, okay, where k here is the weight of the form f. And d mu is the standard invariant hyperbolic measure on the upper half plane. It means that if you pick a subset of x01, then the measure of that subset is given by this integral. It's just the integral of norm f square y to the power k. Okay, and the question is whether there is any pattern as the conductor of gate f gets larger and larger, whether this measure converges to some fixed measure or not. So that's the quantum unique ergodicity problem. Okay, so to formulate it, let's define this discrepancy df phi, which is the measure mu f phi, and we divide by mu f1, which is the measure of the whole x01. So it's kind of a probability measure now. And mu phi is the integral of phi with respect to the hyperbolic measure, the standard hyperbolic measure, and normalized by mu1. Okay. And the conjecture of Rudnick-Zernak was that this df phi will converge to 0 as the weight tends to infinity. Okay. As the weight of the form tends to infinity, the measure, the probability measure mu f phi divided by mu f1 will converge to the standard measure on the upper half plane on the x01. Okay, so this is the quantum unique ergodicity conjecture. Of course, there is a corresponding statement for mass forms as well, where instead of the weight, the spectral parameter goes to infinity. This conjecture was proved by Holowinski and so. But what they got is a very slow rate of convergence. So they had a very, they have a small power of logarithmic scaling. Okay. What we are interested today is trying to get an effective QE. Okay. So we want to prove that there exists a delta positive such that df phi decays like k to the power minus delta. So it's a power saving that we are talking about. Okay, so that was in the weight aspect. Now let us formulate the problem in the level aspect. Okay, so here you take a level, say Q, and you can consider the congruent subgroup gamma naught Q, and let F be a holomorphic cuspidal new form of weight K for that gamma naught Q. Here the weight K will be fixed and Q will be tending to infinity. Okay, now we have the standard inclusion map from gamma naught Q to gamma naught 1, which gives rise to a natural projection from x naught Q to x naught 1, right? So that means any function on x naught 1 can be composed with this projection to get a function on x naught Q, right? So now given any F like this, holomorphic cuspidal for gamma naught Q, we'll find a measure mu F on x naught 1 by if you pick any function, a measurable function on x naught 1, then you define mu F phi to be this integral of phi z, same integral, but instead of integrating over x naught 1, you're integrating over x naught q. Okay. And again, mu here is the standard hyperbolic measure of the upper plane. Okay, the conjecture here is that as the weight remains fixed and the level goes to infinity, then again the discrepancy, which is the difference between the corresponding probability measure and the standard probability measure on the upper plane, goes to 0. Okay, or the probability measure associated to F weakly converges to the standard uniform measure on x naught 1. Okay, so this level aspect version was formulated first by Kowalski, Michel, and van der Kamp. Okay, and this was proved by Nelson in 2011, and then again by Nelson, Pitale, Shaha in much more generality in 2013, using the approach of Holowinski and Sundararajan. Okay, but again, we want an effective statement. So again, we want to show that df phi not only goes to 0, but it goes to 0 quite fast. Like there exists an delta positive, such that df phi decays like q to the power minus delta as q goes to infinity. Okay, so yeah. So the effective QE is in fact known in this case. So it's not known for square free level, but if you take a powerful level, then the work of Nelson, Pitale, and Saha gives you an power saving. So they show that this frequency is bounded by the level by the radical of Q, which radical means that it's a product of all the primes dividing Q to the power minus delta. So if Q is powerful, say Q is a square, then you have like square root of Q over here to the power minus delta at least. Okay, so so now our target today is to give a statement like this and try to give a quick analytic number theoretic proof of that result. Okay, so what we'll do is we'll restrict ourselves to levels which are prime powers, p to the power j. We are going to avoid the following 4 powers. So it's not a prime, it's not a cube of a prime or 5th or 7th power. Then we'll be able to prove that df phi is bounded by p to the power minus 1/6 plus epsilon. So it will give a power saving. Okay, so now let us recall what was the approach that was used by Holowinski and Sundararajan in their first proof of QE in the weight aspect. Okay, there are 2 different approaches. Okay, so again, what we want to show is for any measurable function phi, df phi is going to 0. But instead of doing it for all measurable functions, we can restrict ourselves to a collection of functions which spans the space, right? For example, we can pick phi to be the collection of incomplete Poincare and Einstein series. Okay, here is one example of an incomplete Poincare series. You take h to be a compact, smooth function on 0 infinity, and you define an m an integer and define phm to be this. Okay, if m is not equal to 0, then it's a Poincare series. For m equals to 0, it's the Nash. Here, Ez is of course e to the power 2 pi I z. Right. So now, if you assume that f is now L2 normalized, so mu f already is the probability measure. Then mu f p hm, so instead of phi, we are replacing it by the Poincare series, is given by this integral. And now we can use the unfolding trick because here we have the integral over h modulo gamma naught 1, and here we have the sum over gamma naught 1 by gamma infinity. So by unfolding, this will reduce to this integral, which is quite easy to evaluate because we have a Fourier integral 0 to 1 here and a y integral. So this roughly reduces to the following shifted convolution sum. So here, lambda fn's are the normalized, Hecke normalized Fourier coefficients of f, or you can think of them as the Hecke eigenvalues, the nth Hecke eigenvalue of f. Okay. And so if you use the trivial bound for lambda fn, then you will get that this is bounded by k to the power epsilon. But what you really want to do is you want to show that there exists a delta positive such that this is bounded by k to the power minus delta. Okay, so you want some cancellation in this sum, where the length of the sum is approximately equal to the weight of the function. Okay, so this is the first approach. This was first used by Lua and Sarnak, and it was used by Holowinski in his work also. And his idea was that instead of getting a cancellation in this sum, what he does is he puts absolute value, and then he uses the fluctuation in the Fourier coefficients to have a log saving in the sum. Okay. The other approach is through Watson's formula, where Watson gives, so again here, if we assume to be L2 normalized, you take mu phi square by, there's a Peterson inner product of phi and phi. So here we're taking phi to be any holomorphic cusp form or a mass cusp form or an Eisenstein series of full level. Okay. Because using the spectral theory, we know that any function on the upper half plane which satisfies certain automorphy can be written in terms of these functions, right? So now Watson's formula for phi mass form or a holomorphic modular form or an Eisenstein series relates this probability measure with the special value of a triple product function. Okay, lambda is the completed L function for the triple product f cross phi. Okay. Now, by using the Starling's formula to estimate the gamma factors appearing in the complete L function, one can show that mu phi square is dominated by this L function, L value, L half f cross phi. And this also reduces to sim square f cross phi and L half phi. So this is bounded by k to the power minus half 1 plus epsilon L half sim square f cross phi. Okay. Now, if you use the convexity of the trivial bound for the L function, so since the weight of f is k, the conductor of sim square f is k square, and when you twist it by phi, which is a GL2 form, the conductor becomes k to the power 4. So the convexity bound is k to the power 4 to the power 1/4, so k. So if you plug in the convexity bound, you get k to the power epsilon. So again, you are back on threshold, and it's not going to give you anything. So to get power saving in the decay, what you have to do is you have to get a subconvex bound for this GL3 cross GL2 L function, which is not yet known. But so Sound used this approach, and he could prove a general weak subconvexity result, which gives something slightly better than convexity with a power saving of with a log fractional log power saving. And this together with Holowinski's bound for the shifted convolution sum turned out to be enough to prove the QEV conjecture in the weight aspect, okay, with a small power of log saving. Okay, so now let's move to the level aspect. Okay, and so as I said, that Nelson used the ideas of Holowinski and Sound to prove the level aspect analog of QE. So by replacing phi by a Poincare series, first he showed that the discrepancy can be bounded by a sum like this. So now it becomes slightly complicated. For simplicity, you can forget the L. So there is a sum over cusps. As you vary Q, there will be more and more cusps. And for each cusp, there will be a shifted convolution sum. Okay, and it looks like this. And so here, lambda A will denote the Fourier coefficient of the form at the cusp F. Normalize again. And the number WA, which is going to play an important role here, is the width of the cusp A. Okay, so it's not just a random shifted convolution sum problem. It's a shifted convolution sum problem with a special shift, and that's what we're going to utilize. Okay, and Nelson also established an analog of the Watson's formula, and there he applied Sound's general result, and again, using Holowinsky's idea to deal with this shifted convolution sum, he could establish the QE in the level aspect. Okay, but in the case of powerful level, which was a follow-up paper of Nelson with Amia and Abhishek, they observed that the Watson's formula has a very different behavior here. So if Q is powerful, then there is an extra factor that appears in Watson's formula, which is denoted by JF. And this has nothing to do with this L function. So to get a bound for DFI, you can either try to get a better bound for the L value, which is already a difficult problem, or try to get a better bound for this factor, right? And it turns out that the trivial bound for this factor is such that if you plug in the convexity bound for the L value, then you are again back on threshold. So you need either a non-trivial bound for this multiplier JF or a subconvex bound for the L function. Okay, and they showed using local p-adic analysis that it's possible to get a non-trivial bound for this multiplier with suitable power saving. Okay. So for when the level is powerful, you don't really need to study the shifted convolution sum at all. You can just look at the Watson type formula there, and the bound for the multiplier is already sufficient to give you an effective QE. You don't need to get a subconvex bound, or you don't need to get a cancellation in the shifted convolution sum problem. So the question now arises whether you can prove a similar type of an effective QE using the shifted convolution sum approach. Okay, so that's what we're going to do, right? So let's study the shifted convolution sum problem for level Q equal to p to the power j, where p is prime. Okay, as I said, that there will be several cusps now, and the cusps are given by this. So u by p to the power nu, where nu ranges like this, and u or p to the power nu are co-prime, and u goes modulo p to the power nu and GCD of p to the power nu and p to the power j minus m. The width of the cusp is given by u by p to the power nu. Okay, and so the width of the cusp u by p to the power nu is given by p to the power j by the GCD of p to the power 2 nu p to the power j. Right? And so if you look at the expression that Nelson had bound for the discrepancy in terms of the shifted convolution sum, then if you look at all the other cusps except the cusp at 0, because the cusp at 0 has the widest, is widest, it has the largest width, and so it makes the largest contribution in the sum. Those with smaller widths, because the length of the sum depends on the width. And maybe I missed that point over here. I should have mentioned that here, when you look at the shifted convolution sum over here, the length of the sum, which is n, is bounded by the width. So if you have a smaller width, then the trivial bound is already sufficient for your purpose. Okay, and so you are mostly interested in cusp which has the largest possible width. And then there you need to get some cancellation. Okay, so here it turns out that the 0 is the only cusp which is the largest possible width. The other cusp have smaller width, and you can use a trivial bound for that to bound that contribution by the square root of y by p. Okay, so y is going to be a very small power of p at the end. Okay, and it will be chosen optimally once we get a bound for this one. All right, so that's the problem, and here it's not n, And when you take the width 0, we take the cusp 0, the width of that cusp is p to the power j, which is the level. Okay, so now you want to study the shifted convolution sum, lambda naught n plus p to the power j times L, where n is of size capital N and capital N is like p to the power j, right? So any cancellation in this sum will give you a non-trivial bound for df phi. Okay, so now for the sake of simplicity, we're just going to look at the case where j equals to 2. So we are looking at the case of level prime square. And we want to look at the worst possible scenario where n is largest, n is equal to p square. We're also going to take L to be 1. Okay. Anyway, as said, y is going to be a very small power of p at the end. So, and also we'll be just trivially doing the sum over L. Right? So let's take L equals to 1 and n to be p squared. And let's see what we can do. Right? So we have reduced the problem to showing cancellation in the shifted convolution sum lambda n plus p square, where n is of size p square. Okay. All right. So our method is based on the delta method, so which has been used several times to deal with shifted convolution sum. So delta here means that for any integer n, delta n is 1 if n is equal to 0, and it is equal to 0 otherwise. Right? So now here we'll do a level lowering trick. So we have the equation m equals to n plus p square. Right? So let's factorize this equation through a congruence, which is m is congruent to n plus p square modulo p, or m is congruent to n modulo p. Okay, and if you put this congruence, then the delta is, the equation will be just n minus m minus p squared divided by p equals to 0, because you already know that this is divisible by p, so you have to just check that this divided by p equals to 0. Okay, so now we'll be using a Fourier expansion for this delta symbol. And we are using here a version given by Duke, Friedlander, and Ivanich, and which is just a Fourier expansion of delta n. It looks like this. It may look slightly technical. The thing is that, so there is the Q plays the role of a modulus. And if you take the optimal choice of this Q, turns out to be the square root of the size of the equation. So if you're interested in knowing whether whether n is 0 or not, and if n is running between minus 2m and 2m, then you will pick Q to be 2 square root of n. Okay, that's the optimal choice. Okay, and so the only thing which is not explicit over here is this function gqx, but you can quite easily show that the L2 norm of gqx is q to the power epsilon, okay, for any q. All right, so that's the standard DFI delta method. So we're going to plug in this formula right over here for this delta n minus p squared divided by p. Right, that's what we do. So now our q, okay, let's see what q should be. So n, m, and p square all of them are of size p square and divided by p. So the equation that we are looking at is of size p. So the modulus should be taken as square root of p. So we pick our capital Q to be square root of p, right? And then this s naught p square turns out to be this sum, right? We still have the congruence, n congruent to n modulo p over here, right? So Q is like square root of p. And now we detect this congruence congruent to n modulo p using multiplicative character. So we introduce a sum over chi modulo p with chi n, chi bar n here, right? So now we have completely dissolved the starting equation m equals to n plus p squared using additive characters coming from the circle method or delta method, and multiplicative character modulo p, right? Right, now if you estimate this thing, so this is S naught p square, is an expression for S naught p squared. If you estimate this trivially, that is estimate all the sums here trivially, then you'll get p to the power 4. But we want to show that this actually is more than p squared, right? We want to show that it's bounded by p to the power 2 minus delta. So our job here is to save p to the power 2 plus delta. So it's saving p squared and some extra power of p, right? Now let's focus on the generic Q, right? So take small q to be like capital as large as capital Q, which is the worst case scenario, and capital Q, recall, is just root p. And then our problem is to get sufficient cancellation in this. Okay, so when your small q is like capital Q, there is no oscillation in this x integral over here. So we are going to just ignore that. So because if small q is like capital Q, then you'll have a q square over here, and q square is p. So the denominator is like p square, and the numerator is also p square, okay, because x is bounded by p to the power epsilon. Beyond that, the g function is small. Okay, so we drop those, when you're looking at small q as large as capital Q, we can drop the analytic part because the problem is completely arithmetic. And so we just look at this. I have also conveniently dropped here GQX because what we really need about GQX is that the L2 norm is bounded as like 1 on average in the L2 sense. All right, so we have now these 5 sums, and we want to save p squared, right? So as you can guess, it's a great time to use Voronoi summation formula because n and m have been separated. And then there is an additive character over here, multiplicative character. So if you look at the n sum, we'll have lambda fn chi n e of an by q. So we'll be applying Voronoi to the form h, which is f twisted by chi. And now there is something going on over here because recall f has level p square and trivial Niventipus, and chi is modulo p. So they are not, the conductors are not co-prime to each other. They are actually concentrated on the same, they're ramified at the same prime. Okay, so you have to be a little careful over here, but it turns out that it's still a new form of level p square and Niventipus chi square. And so if we apply Voronoi summation formula to the n sum, it will transform the sum to something like this, right? It will come with the root number over here, which will be the Atkin-Lehner pseudo eigenvalue. All we need is that its absolute value is 1 and nothing else. And and the dual length here will be p, because as I said that the form itself has level p square, and q is of size root p. So this sum has conductor p squared times q squared, which is p to the power 3. So the dual length will be the conductor by initial length, which is p to the power 3 by p squared, which is p. Okay, so this is what you get, and this is p by q is the balancing factor. So if you estimate the initial sum, this is trivially, this is p squared, and this sum, if you estimate trivially, will give you p to the power 3 by 2. So you have saved a root p in the application of the Voronoi summation formula. If you do the same thing to the m sum, you can save root p over there. And applying Voronoi summation formula to both n and m, we will arrive to an expression like this, where you will have a character sum, which will involve the pseudo eigenvalues, that multiplicative characters, the additive characters, modulo p and modulo q, right? And now you'll see that since f was twisted by, in the m sum, f was twisted by chi bar, and in the n sum, f was twisted by chi. So when you apply Voronoi to the m sum, you will have lambda h p squared bar, right? So all you need to know about lambda h p square is that its absolute value is 1, right? So we have a lambda h p square and lambda h bar of p square, and together we'll have absolute value 1, so they will just go away. And you'll be left with a very easy character sum where modulo P is just chi of n bar m, and modulo Q, it will just reduce to a Klosterman sum. Okay, so this is this character sum is phi P times the Klosterman sum. And if m and n are congruent to each other, modulo P. If they are not congruent to each other, modulo P, then it's just vanishing. All right, so we get that S naught P square. If you now, we have to use well bound for the Klosterman sum. So this is bounded by root Q. If you plug that in over here, so this is bounded, the character sum is bounded by P times root Q, but you have a n congruent to m modulo P. And so if you say, if you assume Deligne bound for the Fourier coefficients, then you'll see that this is bounded by this sum. And if you evaluate that, you get P to the power 7 quarter. But if you don't want to use Deligne, then of course you can do Cauchy and use Ramanujan on average, and that will give you the same thing at the end. So you get that S naught, the shifted convolution sum, S naught P square is bounded by P to the power 7 by 4 plus epsilon, which is smaller than P square. Okay, so we have a power saving. And the same trick works if you take any power of Q to be any power of P. And if you just concentrate or focus on the cusp at 0 and trivially estimate the contribution of the other cusp. If you want to have a better result, a better power saving, then you have to also get non-trivial bound at the other cusp as well, and which is also possible using the same trick. Okay, so with that, I will end, and happy 70th, Ram. Thank you.